theories. So please start.
Okay, thank you very much. It's a great pleasure to give this talk at KIS, even though remotely. So I will tell you about work we did in the context of dark matter candidates in confining gauge theories. And the motivation for this is that confining gauge theories that provide automatically good dark matter candidates, as I will show. So by now there is a very strong evidence for the existence of matter beyond the standard model, that is dark matter, and this evidence comes from very different gravitational measurements, and it's a very well established fact that to explain this all this data. You need a new non-baryonic and non-relativistic component of matter that as energy density is about 25% of the energy density of the universe, and also 5 times the energy density that you see in visible matter. What observation don't tell us, however, is what dark matter is made of, and this is the reason why there is a huge number of models that people have proposed to explain dark matter, and at the moment, from observational point of view, is very difficult to prefer one type of model compared to the other. So we go from dark matter, which is astrophysical object, for example, a primordial black hole, to extremely light scalar with mass of the order 10 to the minus 20 electron volt. So it's clear that to have an idea of what dark matter actually is, you need some theoretical guidance beside experimental data. So this is the motivation of the talk. So in particular, I think a very important theoretical hint is the fact that dark matter must be stable and it should not decay. So this is important for the following reason. So you know that the proton lifetime is extremely long. In fact, we have never seen a proton decay, and this gives an upper bound on the lifetime of the proton, which is 10 to the 34 years. Now, in the standard model, there is an extremely good reason for this stability, which is accidental binary conservation of the standard model Lagrange. That is, if you once you specify the quantum numbers of the particles in the standard model, automatically the theory has a U1 symmetry, which is baryon number, which corresponds to the rotation of each quark with the same phase. So this symmetry guarantees the stability of the lightest baryon in the theory, and so explains why the proton is stable. Once you go to beyond the standard model, this symmetry can be violated, and it can be violated at the lowest order through dimension 6 operators. And this gives a lifetime of the proton, which is compatible with experimental bounds if the standard model is valid up to, for example, the unification scale. So when we go to dark matter, we also want a stable particle, but the way cosmological stability of dark matter is typically obtained is completely different because it is obtained by assuming some global symmetries, either discrete symmetries or global or continuous symmetries. So the chief example in this class is a supersymmetry. So in supersymmetry, you can impose a discrete symmetry, which is R parity. And under this R parity, the standard model particles have a positive parity, while the supersymmetric particles have negative parity. So because of because of these disparities, automatically the lightest supersymmetric particle is stable, and it is a dark matter candidate. However, our parity in supersymmetry is not a property of the theory. It's not an automatic feature of the theory. It's something that you have to impose from outside. So by looking to the standard model, this is not exactly the most attractive case for dark matter. And so I think a very natural question is whether dark matter can be accidentally stable as the proton is. So if you try to answer this question, you see very quickly that essentially, in order to generate accidental symmetry, you will have to introduce a new gauge forces that I call dark forces. And in this context, then the simplest realization of dark matter is dark matter as an accidentally stable hadron of a dark sector. Okay. So what I have in mind is something very concrete, which is a confining gauge theory with new fermions. So these new fermions are charged under the new gauge group, and they're also so I will assume also that they are charged under the standard model, so they interact through standard model interaction, gauge interactions with the standard model degrees of freedom. And possibly, if the quantum numbers allow, you can also have Yukawa couplings between the standard model Higgs and these new fermions. For a slightly technical reason, these fermions will have to be vector-like, meaning that you can add the mass term to the Lagrangian. And the reason for this is that if you make this assumption, then this sector does not break electroweak symmetry. Okay? So this is not a theory of Technicolor in any way. Okay? It's more like QCD from the point of view of QED. So the Lagrangian for this theory is you can write it on a line as the standard model Lagrangian. So it's just essentially fixed by the quantum numbers of the new fermions under the dark gauge group, which I call dark color, and under the standard model. So this is nice from the point of view of accidental symmetries, because once you have a gauge theory, you automatically have accidental global symmetries. So the first one, the first global symmetry is a dark baryon number. So this is the rotation of all the quarks and of all the dark quarks with the same phase. And by the same reasons as the standard model, this guarantees that the lightest baryon in this dark sector will be stable. You can also have dark species number. So if you have multiple representations of the multiple irreducible representations, then you can rotate different quarks, different fermions with different phases. And this leads to the stability of the lightest meson in the theory made of different species. Yeah. So this should be familiar, is related to the fact that, for example, the pi plus is much more long-lived than the pi zero in the standard model, okay? Because pi plus is made of up and down quarks. There can be also discrete symmetries that are called G-parity, but let me not go into that detail. Now, from the point of view of dark matter dark baryons are the most attractive candidates because they are very robustly cosmologically stable. Okay? So they decay at the level of dimension 6 operator or even higher, depending on quantum numbers. And if you consider what is the lifetime of dark matter here, okay, so this is not the lifetime of the proton, the lifetime of dark matter, you see that this is compatible with the constraints that we know, okay. For example, for dark matter, which is of the order 100 TeV with a UV scale, okay, is of a dimension 6 operator, which is over the order of the Planck scale. Okay. So in this talk, I will mostly focus on the possibility that, well, in the first part, I will focus on the possibility that dark baryons are the dark matter candidates. You can also play with pions, so with the lattice meson. In that case, the cosmological stability is however, less robust. So you can actually build many models of this kind, and the goal here will not be to go into the details of this model, but I just want to give you a flavor of the type of models that you obtain. Okay. So essentially, the models they depend on the quantum numbers of the new fermions, and so for example, if the new fermions are in a complex representation of the gauge group. So for example, the fundamental of SUN. Then you have that the baryons, so the dark matter will be a baryon, and the baryons and antibaryons are different particles. Yeah. So this means that you can produce them, for example, through as a thermo freeze out, or also through an asymmetry as in the standard model. If the representation is real, for example, the fundamental of SON, in this case, actually baryon and antibaryons are the same particle. Okay, so this means in particular that you cannot make an asymmetry between particles and antiparticles. And also, in this case, what you find is that the direct detection constraints are very weak because dark matter will be a Majorana particle. There is a slightly different class of models which will become relevant in the second part of the talk, which is when the representation is an adjoint. In this case, instead of a baryon, you can do a bound state of the adjoint fermion and the gluons and the gluons. Okay? So this has a bit different properties from a baryon, but from the point of view of cosmological stability is quite similar, and you can also build models with this type of representations. So the other important distinction is the masses. So you can consider models where the mass of the quark is less than the dynamical scale. So this is the situation in the standard model for up and down quarks. So in this case, you find that dark matter is a baryon in the dark sector, and it is intrinsically strongly coupled, okay, as the proton and the neutron are in the standard model. So the dynamics of this theory is quite complicated, but on the other hand, the dark matter story will be, in particular the cosmological history, will be rather simple. Okay? Not too different from a weakly interacting massive particle. You can also consider the opposite limit, where the quarks are larger than the dynamical scale. In this case, you are in the heavy quark is like a charm or bottom in the standard model. And so the bound state that you will make of quarks, they are actually perturbative non-relativistic bound states. So the dynamics of this theory is much easier to establish. But as it turns out, the cosmology, in fact, is much more complicated than the previous case. And it is also model dependent. It depends in particular on these two scales that you have in this regime. One is the dynamical scale where the theory confines, and the other is the Bohr radius of these bound states. Okay, so let me give you a little more details on the light quark regime. I will mostly focus on this. So mass of the quark less than the dynamical scale. So the spectrum of this theory is the following. So we assume dynamics as QCD. So the lightest states are pions. And then you have, well, you have other mesons that are unstable. And then you have baryons. And the baryons that will come in multiplets of the flavor symmetry. And these multiplets will be split by standard model interactions, gauge interactions, and Yukawa interactions, with a splitting that you can estimate as Mehara-Lagrange, is of this kind. All these quantities are quantities in the dark sector, obviously. Then so from this you get standard model multiplets, and out of this, each multiplet will be further split by electroweak symmetry breaking. And this electroweak symmetry breaking gives you a splitting of order 100 MeV. So at the end, you're led to a tower of baryons, and what you know from first principles is that the lightest baryon in this theory will be stable, and it is your dark matter candidate. So the question then is, what are the quantum numbers of this baryon, and if they are compatible with the constraints that we have on dark matter? Okay. So you can do this, for example, in SUN. Okay, so you can take SUN gauge theory with an F light flavor. And these flavors, they come in a representation of the standard model, for example, triplets or doublets of electroweak symmetry. Then the dynamics of this theory, we assume for now that it is like QCD, so you have a chiral symmetry breaking. And importantly, because I will take fermions which are in a vectorial representation, you can check that the vacuum does not break electroweak symmetry, which is important for knowledge. So out of this, you will get the number Goldstone bosons, and as I mentioned, you can build the dark matter models with these dark pions, which will behave to a large degree like elementary particles for what concerns dark matter. So, for example, if you have a stable pion, which is a triplet of SU2, you find that the thermal abundance is, as for the Wino, of the order of 3 TeV. As I mentioned, dark pions are less attractive from the point of view of accidental symmetry and cosmological stability. So I focus on baryons. So here, as we said, we are interested in the lightest baryon. And so baryons, you can more or less establish this by generalizing the 8-fold way of strong interactions. So in particular, you expect the lightest multiplet to have the lowest spin. So this determines the flavor representation. And then you can decompose this representation under the standard model and see what are the quantum numbers of the lightest state. Now, if you want to do a dark matter candidate, you want obviously to require that the electric charge is equal to 0. This is one constraint. But you also, in this type of models, you also want to require that because in this case, dark matter is the Dirac, okay, you also want to require that the hypercharge is equal to 0. The reason why this is the case is because if the hypercharge was different from 0, then you would have coupling, three-level coupling to the Z, and this would lead to very strong direct detection constraints that would exclude the model. So out of this, you can do a classification, and this is, for example, the classification of SUN. So the rules are the following. So you want the SUN gauge theory to be asymptotically free. There should be no lambda opposed below the Planck scale for the standard model couplings, because you want this theory to be valid up to a very large scale. The lattice dark baryon should have 0 charge and 0 hypercharge. And then there should be no stable particles, for example, with electric charge. Okay. So this fixes the, so this gives you essentially a finite list of possibilities. So for example, one simple example is just take fermions which are attributed of SU2. Okay? Then for a number of colors equal to 3, then the baryon you find that it's also attributed of SU2. Okay? So it's what you would call a composite wino, for example. Okay? So triplet of SU2, but composite. So for what concerns the abundance of this dark matter, so simplest option is to do dark matter as a thermal relic. So in this case, the dark matter abundance is inversely proportional to the annihilation cross sections. And so this dark balance, they can annihilate to standard model as usual WIMPs, but they can annihilate strongly to the dark pions in the theory, and this is the annihilation that dominates. Now this is a strongly coupled process, so you expect to give a cross section close to the unitarity bound. And with this estimate, you find that the mass of the baryon is of order of 100 TeV. Yeah. So this is an estimate, but in fact, if you take just the QCD data, like proton anti-proton annihilation, and you rescale, you again find this type of value for the mass of the baryon. Yeah. So this is a relatively robust prediction of this type of models, that the dark matter will be in the 100 TeV range. You can also do the dark matter asymmetric. This requires further model building. In that case, the dark matter could be lower, which is of course welcome from the point of view of experiments. Just a tiny bit of chronology. So this for example, for direct detection, if the dark matter, the dark baryon is a triplet of SU2, then you find that the spin-independent cross-section is the same of an elementary triplet of SU2. However, so so the triplet of SU2 is a very strongly motivated candidate for supersymmetry. And in the elementary case, its mass is around 3 TeV, and this will be accessible to direct detection experiments in the future upgrades. Okay, so it will be around here, for example. In our case, however, the mass, the cross section is the same, but the mass is 100 TeV, so is outside of this plot. And it ends up actually below the neutrino floor, which means that it will not be possible to, this will not lead a signal even in future upgrades of the direct detection experiments with the current technology. So this makes, so in general, the large mass makes the experimental detection more difficult. But there is also interesting effects that could be detected. So first of all, if there is Yukawa couplings, then there can be a much larger signal for spin-independent cross-section, which comes from coupling to the Z, and this actually is a constraint of this type of models. The other interesting thing is that, well, since this dark matter is composite, so it would be really interesting if you can use the features of compositeness to distinguish it from elementary dark matter. So in fact, this is the case because this dark matter baryon has large dipole moments. It has obviously a magnetic moment as the neutron in the EDM, But because you have a theta angle in the dark sector which is unconstrained, it can also have a significant electric dipole. And as it turns out, these they will give interesting signals in direct detection experiments that could be accessible in the future.
Excuse me.
Yes, please.
Would you remind me, as far as the dark matter abundance is concerned, what was the main channel of the annihilation
Yeah, so
processes?
It's a baryon, anti-baryon into dark pions. Yeah.
Uh-huh.
So in the standard model, proton antiproton goes into pions.
Yeah.
With the cross section which is measured is of the order of this value. This value is also motivated by strongly coupled arguments. Yeah.
So you're assuming that there will be some hidden thermal bath which is isolated from the standard model sector.
No. So I'm focusing here on constituents which have standard model charges. Okay.
Mm-hmm.
So this guarantees that this sector is in thermal contact with the standard model. Okay.
Oh, okay. So only SU2L we assume on the.
Yeah. So so here I'm focusing on SU2. So this is model dependent. So for example, you have other models where you also have strong interactions, experiments which are charged strong interactions. But even if the interaction is just electroweak, this guarantees that this sector is in thermal contact. Okay. So
I see. And okay. So, and then for the dark mesons, dark pions, they seem to be decay into standard model Higgs bosons,
yes.
or
yeah.
Okay,
In fact, they do. Okay. So yes.
I see. Thank you.
Yeah. Thank you for so it's important. So here I consider a class of models where the constituents they have charges under the standard model. Okay. Otherwise, the sector would be completely dark, and the story, it would be different.
Yeah.
Okay, so just a couple of words on the different. So there is different regime. Mass of the quarks greater than the confining scale. So here the dynamics is very different. So the lightest state, in fact, are gluons, which have mass of the order of the dynamical scale of the theory. These gluons, however, decay to the standard model. Then you have the dark mesons that have mass twice the quark mass, roughly, and then you have the dark baryons, which have mass n times the dark n times the mass of the quarks. Okay? Now, the stability argument is still valid in this theory, and so the lightest baryon again will be stable in this theory. And in fact, it is a perturbative object that you can study. For example, you can study the spectrum similarly to Botomon, for example. So that part is easy, but this type of scenario actually leads to kind of non-standard cosmology because you have a mixture of perturbative effects and non-perturbative effects. Okay? So, for example, just to give you an idea, so you can have that. So, if these quarks are very heavy, okay, so you have that dark quarks that do the standard freeze out, and then once the theory, once the temperature drops below the confining scale, you have that all the quarks they recombine in color singlets. And so you're interested, in, for example, in what fraction of quarks recombines into baryons in order to establish how much is the abundance of dark matter. Then there is so after you form this after confinement, often you find bound states which are large, okay, size-wise. And so this leads to a strong annihilation cross-section that can modify the abundance. And further, there is this group also that they decay through high-dimensional operators. So they decay through loops of standard model fields with standard model fields. So they're typically long-lived, and so this can lead to entropy injection in the standard model plasma that dilutes the standard model amounts, the dark matter amounts. So this is a bit the cartoon of what happens. So the end result in this regime is that dark matter can be much lighter than 100 TeV, let's say in the 10 TeV regime, and with homology which is very different. Okay, so this was a bit review of past work. Are there questions about this part before I move to the more recent work? Okay, so let me now talk about this this new work that I wrote in August, which is a different realization of dark matter in this in confining gauge theories that had been overlooked before. So all this work that I described, and also not just by myself, but also by other people, okay, assumes QCD-like dynamics, which means that you assume that when the coupling becomes non-perturbative, you have confinement and also chiral symmetry breaking. Now, long ago, Toft argued that strongly coupled gauge theories may have different behavior, and in particular, they may confine without chiral symmetry breaking. And if this happens, then you have spectacular predictions. So, because the matching of quantum anomalies of global symmetries requires the existence of massless composite fermions in the chiral limit. Okay? So, if the theory is massless, then you can argue that some fermions must be massless despite the fact that they are composite. And by the way, this subject has been revived recently due to new results by Seiberg and collaborators, where they showed that the new anomaly matching condition exists from gauging of a higher form gauge symmetries. And so this puts a further constraint on the dynamics of strong coupled gauge theories. So what are we considering in the context of dark matter is precisely fermions which arise from anomaly matching in strong coupled gauge theories. However, to do dark matter, these fermions they have to acquire mass at some level. And this will be done by adding some small explicit breaking of the global symmetry of the theory, okay? As I will show in an explicit example. Now, why is this interesting for dark matter? Well, very simply, the lightest composite fermion in a dark sector is automatically stable because of fermion parity, okay? Even without talking about more complicated symmetries. So if you have a dark sector with the lightest fermion, this will be stable to some level. So the decay will be induced by high dimensional operators which connect this state created by an operator of dimension d1 to some states of the standard model that I describe it as an operator of dimension d2. Yeah. So if the product of these two operators has dimension 6, okay, then you find this lifetime, and this lifetime is compatible with the stability of dark matter for lambda, which is not too large, and this sorry, for lambda UV, which is not which is at least the Planck scale. So this is essentially the same lifetime that I wrote for the baryon, except for the fact that in this last bracket I have the mass of dark matter rather than the confinement scale. Okay. So this implies that the lifetime of these states are in fact enhanced compared to the one of the baryons And so in this context, it's always a welcome thing if dark matter is stable. So the spectrum in this theory will be vastly different from the previous ones. So I have so there is a confinement scale, lambda dark color, where you have all the composite states, and then there will be some fermions which are parametrically lighter than lambda. Okay, so there will be a large separation between these two. So these light composite fermions, I will show they are very good dark matter candidates, and they behave very differently from the composite dark matter that I described before. So essentially, quite similar to pions, if you go to energies much below lambda, they behave very much like elementary dark matter. Okay? So they behave. So the only difference will be high dimension operator suppressed, which give an effect energy divided by lambda. So in particular, if you want to consider the thermal abundance, what you want to know is the annihilation cross-section of the states in the standard model. So the states that can only decay in the standard model, because they are the lightest states in the dark sector. And so this annihilation cross-section will be the one that you compute for an elementary particle, plus corrections which go like m squared divided by lambda squared. So this in particular implies that the abundance is to leading order the same that you have in the standard model. And so this means that, for example, if your fermion has quantum numbers, electric quantum numbers, the thermal balance will be reproduced in the TV range rather than in the 100 TV range. Now, this should not give, however, the impression that compositeness is irrelevant in this theory, because there is 2 or 3 places where, in fact, is very important. First of all, when you consider explicit models, often you find composite fermions which are singlets of the standard model. And in this case, all the interaction, so the lead interaction is the one due to compositeness. Okay? So this will lead, in fact, to very strong constraints of singlets. Moreover, so when you have multiple states, what you find that these multiple states are stable at a renormalizable level, and so they could give, for example, multi-component dark matter. However, composite effects, they allow the decay of heavier states into the lightest one, and so this lifetime is very important for the phenomenology, because so depending on the value of lambda, you can have a very different scenarios. So let me give you. So I would like to give a couple of examples. So the first one is this theory, SU engaged theory with 3 adjoint fermions. And I will take these 3 adjoints to transform as triplet of SU2. Okay. Now, we actually wrote a paper about this with my collaborators in 2018, and we assumed that the standard pattern of chiral symmetry breaking, which in this theory would be SU3. So the global symmetry is SU3, and it breaks spontaneously to SO3, providing 5 Goldstone bosons. And in this case, the lightest fermion would be what we call the glue quark, which is a bound state of the triplet fermion and gluons. Now, in the standard pattern of symmetry breaking, you expect this fermion not to be massless, but to have mass the maximum between the dynamical scale and the mass that you put in the Lagrange for this fermion. So we worked out the phenomenology, which is quite interesting. and I don't want to go in the details here. So the end result is that as for baryons, the dark matter is typically very heavy. Okay? So for completely different reasons, last year, however, Popis and Ritov argued that this theory may have precisely the dynamics described by Toft, that is of confinement without current symmetry breaking. And if this is the case, it changes completely the results that we wrote in the previous paper, and actually in a quite interesting way. So let me tell you about this paper of Popis and Ritov. So what they showed is that so the anomalies, the global anomalies of the theory, Toft anomalies and discrete anomalies, they can actually be meshed by n²-1 composite fermions, which are triplets of SU3, of the SU3 global symmetry. And so they correspond to these operators, which are well, basically strings of gluons attached to the fermion. Okay. So this has the right ingredient for realizing confinement without current symmetry breaking, and is one of the most compelling examples, I think, in non-supersymmetric gauge theories. So if you take this model and now you try to build a dark matter model, you also want to add the mass term for these fermions, and I will take this mass term much below the dynamical scale. So once you put this mass term, you find that so this mass term breaks explicitly the SO3 symmetry to SO3, and gives a mass to the composite fermions. Which will be, so there is no symmetry argument why they should be degenerate, so they will be proportional to the mass of the fermion in the Lagrangian times probably order 1 numbers, which depend on the strong dynamics. So this, let's assume this. So if this is the case, now the story for dark matter is vastly different, because instead of having one triplet, so if I take gauge theory SO3, instead of having one triplet, I have 8 triplets that I call Wino-like. So Wino is a triplet of SO2 that are the dark matter candidates. Now here comes in the higher dimension operators. So these fermions, they can decay into each other, so to lead in order, they can decay through dimension 7 operators, which are suppressed by the confinement scale. Okay, so this is an effect which is in the theory. It's not. It doesn't depend on UV assumptions. Okay. It's difficult to compute, but it is unavoidable based on symmetries. So this leads to a lifetime that I brought here, and so depending on the value of lambda, you can have a very different lifetimes, and this changes completely the phenomenology. So, for example, if you have lambda which is greater than 10 to the 11 GeV, then you find that all the triplets are stable. In this case, you have multi-component dark matter, and what you find that the thermal abundance of dark matter is produced for masses of the order of 1 TeV. Okay? So lighter than triplet of SU2. Okay? So there is just a factor root square of 8 that reduces the critical mass. So if the mass is a bit lower, okay, then the lifetime of the states are still very long compared to the age of the universe, but a fraction can decay. So this maybe is interesting for astrophysical signals. If you have if you go below, then all the heavier states they decay early on. Okay, and so the dark matter today is made of the lightest of these states. However, the lighter states, they still contribute to the dark matter abundance, and so you're again led to dark matter which is somewhat below 3 TeV. If lambda is less than 10 to the 5 GeV, then the decays become really fast. But they can be, so this can still change the abundance of dark matter if the splitting are very small. Okay? So this is something that depends on the dynamics, how much is the splitting. And, so it's, we cannot say from on general grounds. So this would be actually interesting for indirect detection. So let me tell you, so for a triplet of SU2, okay, which I call WINO, is so the thermal abundance is reproduced for mass 2.9 TeV, and this leads to annihilation into photons, which is somewhat in tension with astrophysical constraints. Okay? So this is a debatable thing because it depends on the distribution of dark matter. But let's say that well, there is some discussion that this might be even excluded. Now, in our case, we are more in the range of 1 TeV. So this is less problematic from the point of view of constraints. But in fact, what is more interesting is that, for example, if you have the scenario where all the states are stable, then each of the states would annihilate to photons of slightly different energy. So this will give really a spectacular signal of multiple photon lines at the TeV scale that it would be really exciting if one could see that. Okay? It would distinguish it from many other models. The other interesting thing for technology is that these composite triplets, so they end up around the TeV range. And this is somewhat easy for future collider, 100 TeV collider, while a 3 TeV triplet is very challenging. In fact, being at 1 TeV and also with some multiplicity, factor of 8 multiplicity, is not even a hopeless high luminosity LHC, perhaps. So this was one example. Let me go to the next example. So with these examples, I want to give an idea of the type of scenarios that can arise in this context. Okay? It's not so you can build many other scenarios, in fact. Okay. So let me consider now this theory, which is a SON gauge theory with n-4 flavors and 1 adjoint. Okay? So these are the degrees of freedom. So as it turns out, this theory can have confinement in vacuum carrier symmetry breaking because anomalies can be matched by a fermion, which is in the symmetric representation of the global symmetry, and is made of 3 fermions. So fundamental, adjoint, and fundamental. And you can work out the Carol Lagrange on this theory. So once you introduce the mass terms, and you find that it depends on 2 parameters of the storm dynamics, which are these A1 and A2. Okay? That control these effective operators for the composite fermions. So let me give you first example. Okay, so let me take now number of flavors equal to 3. Okay, and these fermions will transform again as a triplet of SU2 of the standard model. Now the composite fermions are in the symmetric representation, which is a 6 of SU3, and this decomposes as a singlet plus quintuplet. Okay? So in this model, you get as a composite fermions a quintuplet. So a quintuplet, in fact, is a good candidate for dark matter that people have considered. It's called minimal dark matter, and also a singlet. So the dark matter will be the lightest of these two states, and who is the lightest is in fact determined by these coefficients. So I cannot say from first principles. Now this model is interesting because it contains a singlet, and as I said, the singlet interactions are completely determined by the composite scale. And in particular, the annihilation cross-section, it goes like, of the singlet goes like 1 over lambda square. And this implies that there is so if lambda is large, the abundance of the singlet is very large. So this is what is shown in this plot. So here I'm assuming that the dark matter is the quintuplet, and the singlet decays into the quintuplet. You see that if you increase the confinement scale, you find that the abundance is too large because of the overproduction of the singlet. So this shows you one place where it is very important, the composite effect of the states. You can build more models. For example, you can take 5 flavors that decompose as Higgsino, so as a doublet of the standard model and a singlet. So these are same quantum numbers of Higgsino and Bino in supersymmetry. And at the level of elementary Lagrange, you can write mass terms and you cover interactions. So in this case, you find that the composite fermion contains these degrees of freedom. So it contains doublets, triplets, and singlets. And so it looks a lot like a composite neutralino system, except that there is some extra states. Okay. And so you can play essentially the game that you play for neutralino style methodology, and the crucial parameter that enter, besides the one that you see here in the Lagrangian, are these parameters of the strong dynamics A1 and A2 that you would like to determine. So since I have a little, still 5 minutes, I think, can I take 5 minutes more?
Sure.
Okay, so I'm almost at the end. Okay. So the main assumption here is that in this theory, it is possible to have confinement without Archimedes breaking, but I cannot prove for you that this is actually realized. Okay? And in fact, there is no example, no supersymmetric example that where confinement without Archimedes breaking has been proved, unfortunately. It's a possibility, but is not fully established. So because of this, it's interesting to look at supersymmetric examples, because in supersymmetry you can actually prove. So there is canonical examples where you prove that the theory has confinement to Walker symmetry breaking. And this goes back to the work of Seiberg in the 90s. And starting from here, you can also build a composite dark matter model, as I will outline in the next couple of slides. So to give the idea, so the simplest example where you have a confinement without current symmetry breaking is an n equal to 1 supersymmetric gauge theory with the gauge group SUN and number of flavors, which is n plus 1. Okay? So capital Q's are the elementary degrees of freedom. Okay? What Seiberg showed is that all the anomalies are meshed, and they gave very convincing arguments that confinement without symmetry breaking is realized, where the composite degrees of freedom are small q and small q tilde, which are baryon-like combinations of the fundamental fields, plus that transform as fundamentals of SU left and SU right global symmetries, and a meson which is in the UV theory the product of Q and Q tilde, which transforms as a bifundamental of the global symmetry. So this is the work of Seiberg in the 90s. So this actually became later on in 2006 it was actually showed that this and other theories also break spontaneous supersymmetry once you include the mass term, a supersymmetric mass term for the elementary field. And from my point of view of accidental symmetry, this is something that I would want to do anyway. Okay, so is a welcome feature. And you can establish this by looking at the low energy effective theory in terms of these composite degrees of freedom, where it is described by a superpotential which has this trilinear term, okay, plus this term which is linear in the meson field. Okay, is proportional to the mass in the Lagrangian and proportional to the meson field. So with this superpotential, you can find the vacuum, and you discover that the vacuum breaks supersymmetry because the energy is greater than 0. And in the simple example of the general masses, then you find that the vacuum has meson field, so the meson field has no value, while one component of the baryon fields are different from 0. And this at this level you find a set of massless particles. So you find in fact Nambu-Goldstone bosons from spontaneous symmetry breaking of the global symmetry. You find the composite massless fermions which are contained in these components of the Caro field M. And you also find a Goldstein. Now, to build a dark matter model, then you will want to add explicit supersymmetry breaking to this theory. That is one option. And once you do that, all these fields they will acquire a small mass, and then you can build you can start the phenomenology of the model. Just to give an idea, let me consider in this context a theory where the fermions, the elementary fermions transform as a triplet of SU2 and a singlet. In this case, you will find Nambu-Goldstone boson which are two triplets and a singlet, and you will find the composite light fermions which are a singlet, a triplet, and a quintuplet. So we are actually looking at this theory right now. So the phenomenology will be somewhat different from the one I described before, but it can be analyzed with similar methods. There is one important thing that happens once you add scalars, is that at this point the cosmological stability is less robust. Because so the composite fermion, which is for example could be like a bound state of a which is a bound state of a fermion and a scalar, okay, has dimension. So in the UV theory, it has a dimension 5 alpha. So it could in principle decay through dimension 5 operators. Okay, so this could change. So this could make the cosmological stability less robust, okay? And I think this is also a general feature of the theories with scalars. But the important point here was to give you one example where you can actually prove confinement without chiral symmetry breaking. Okay, so let me just jump to the conclusions. So I think there is a strong theoretical motivation for dark matter, which is accidentally stable. And this very nicely realized if dark matter is charged under a dark gauge group. And in this class, probably the dark baryons are the simplest dark matter candidates, which are very robustly cosmologically stable. So I described a bit the homology of this, the possibility that you have in this model. There is really a lot of homology that I did not have time to go through. So what I described in the second part is a different possibility, which is quite exciting, which relies on the possibility that confinement, you have confinement without arithmetic breaking. And in this case, what you find that the lattice composite fermions is your dark matter candidate. This is also cosmologically stable as the baryon, but the phenomenology is completely different and interpolates between an elementary behavior and the composite dark matter. This is very exciting from an experimental point of view because the mass is typically in the TT range, so it's much more accessible experimentally, and you can have exciting new signatures such as the multiple photon lines in indirect detection experiments, as I described in the talk. So there is many follow-ups of this work. Obviously, what we would like to have is a better understanding of astronomodynamics, which is necessary to determine whether you have a confinement without arithmetic breaking. And this is possibly it could be possible also to make progress on the lattice, where this theory you could study whether this confinement without arithmetic breaking is realized. Okay? In fact, I think there is some work in the context of SUN with linear joints. I didn't go into the details of the phenomenology, but it's probably interesting to do so. Another direction is to add scalars, because this will lead to new classes of theories. And the simplest example is supersymmetry, where you can actually establish confinement without arithmetic breaking. So thank you very much. I'll stop here.
Thank you very much for the nice talk. So, question?
Hello, I have a question about the next lattice state in the baryon state spectrum. So you assume that the consistent fermions are SU2 doublet, right?
Well, the example that I really gave was triplet. Okay, but
okay.
In a different model, I can do doublets. Okay.
I see. Well, nevertheless, there should be the isospin partner of the lattice one, which is like corresponding to neutron in a standard model, and which eventually decays into protons. So I'm wondering if it will be long lifetime. I mean, the late decaying state.
Okay. Thank you for the question. It's an interesting question. So the spectrum is the following. Okay, so so here we are talking about the splitting between different multiplets of baryons. Okay. So the splitting is m-pi square, so it goes like m-pi squared divided by the mass of the baryon. Okay. And so this is quite large. So I think this states the decay quite fast typically, okay? Because the mass of the pion is not that large, not that small. Okay. So this pion here, okay, they're not massless because they are there can be quark masses in the Lagrangian, but the gauge interactions anyway, they give a mass which can be, I don't know, 1/10 of the dynamical scale. Okay, so this splitting is not very small. Okay, it's not very small. So I think these states they will decay quickly enough.
So is that imply the standard model pion mass or dark pion mass?
No, it is the pion mass in the dark sector. Okay.
Okay. Yeah.
Yes.
Mm-hmm.
So it depends on these splittings. The splitting are quite large, and the decay can take place through emission of standard model degrees of freedom, okay, which are light compared to the scale that we are talking about.
Sorry, I don't still get why the splitting could be large, because it's done by just a standard model weak interactions.
No. Okay, no. There is two things. Okay, so there is a flavor multiplet. Okay.
Yeah.
Which is the analog of the the octet of QCD or the decuplet of QCD. Okay? When you put standard model interactions, okay, then these multiplets are split into standard model interactions. Okay, so one flavor multiple will give many standard model multiplets. Okay. Now the splitting inside each of these multiplets is the usual one. Okay, like if it was elementary. Okay, so for example, if you get a triplet, you will get that the charge component is split by 166 MeV. Okay. So the decay of that decay will be the usual one. Okay. It can give you displaced vertices and things like that. Okay. But it's not long-lived from the point of view of cosmology. Okay. Now the other states, the one that from different multiplets, okay, I think they are even more unstable. Okay. Because they decay through they can decay also through strong interactions. Okay, so I think this probably requires a more detailed computation. I don't think that these other states will be stable. Okay, but okay.
Yeah. Well, I just wonder if the next latest state gives a additional entropy injection later times.
Oh yeah. No, I think the decay will be too fast. So this doesn't happen this year. It does happen a lot in the other theory. Okay, in the theory where you have a heavy quarks, these gluons they are automatically long-lived. Okay. And so they do give entropy injection, okay, and this is the reason why in this plot you have this funny shape here. Okay, so, but in the other theory, this I don't think it happens. Okay? The decay is quick enough.
I see. Okay. All right. Yep. Thank you.
Hello.
Hello.
Can I? Hi. Could you show the slide about this singlet composite singlet fermion interaction with standard model field?
I didn't really write. You mean this one?
No, previous the earlier part of the composite fermion.
This one?
No, I think it was previous one. Previous slide. Previous. This guy. Okay, this slide. So here you have a dark matter operator and the standard model operator. And when you write down this operator, do you assume this global symmetry is preserved or not in this operator?
No.
It's
no,
not.
Here the logic that I let anything go. Okay.
Yeah, anything. Okay.
Yeah.
Then,
so for example,
then what will be the dimension of this lightest composite fermion? Mass dimension?
What would be the mass range?
No, mass dimension.
Mass dimension. So in the IR theory, okay, This is just an element. It looks like an elementary fermion.
Yes.
So it will have canonical dimension 3.5. Okay? But in the UV theory, okay, in the UV theory, in this explicit example, okay. So for example, in this example here, okay, it will have a dimension
right.
9.5.
Okay.
And this what this is the reason why you get these very slow decays. Okay.
So could you go back to the slide?
Yes.
Yeah, here. No, here, the previous slide, the dark matter and the standard model.
Sorry.
Yes, this one. So so suppose we consider. I mean, this looks like, for example, Dirac Yukawa term for the right-handed neutrino and the standard model neutrino. So let's assume standard model operator equal to the left-handed lepton doublet times Higgs tilde.
For example, yes,
And
yeah, here I'm doing that.
and that will make in principle make a composite light fermion decay to standard model field, right?
Yes, yeah. In this example, I'm doing that. Yes.
And then if we assume the composite fermion is just looks like elementary field, then the lifetime, I mean, unless this coupling is small, then you will have a very strong decay because it's a Riemann light, dimension 4.
No, but I cannot, in the UV theory, I cannot write.
In the UV theory, it's not, right?
No, yeah, I cannot write. I mean, I had to write a couple in the UV theory. Okay? And it's, yeah, that's the whole trick here. Yes.
Okay. So this operator is written in the UV theory.
Yeah. So
and then you take a matrix element in the between the vacuum and
precisely. Yes.
Okay.
Yeah.
Okay. Thank you.
Yeah. This is very important. Yes.
Any other question? If not, then let's thank speaker.